Here's a traffic light suspended on a wire over a street. I'd like you to pause the video for a second and sketch a free body diagram for this traffic light. Anyway, so I hope this free body diagram is close to what you came up with. Obviously the force of gravity acts downward, and we've got tension running along the wires in these two directions. And there's two tension forces. Ft1 and Ft2 are neither x horizontal or y vertical. They're both. We have to follow the Vegas rule. What happens in x stays in x, what happens in y stays in y. So in order to figure out about how the forces are adding in two dimensions to make this traffic light stay in place, we're going to have to break these vectors down into their components. And there are the components. So Ft2 can be broken down into its vertical and horizontal. Ft1 can be broken down into its horizontal and vertical. Just like we saw with motion now, what we really need to do is add up these components separately. Everything that's in the vertical dimension, which is Ft1y, Ft2y, and Fg, will go together. And then everything that's horizontal, Ft1x and Ft2x, will go together. So that's not hard to do. We just do sigma F equals ma. And like we did with projectile motion, we just do two problems. One for horizontal, sigma Fx, and one for vertical, sigma Fy. So when you look at your free body diagram, you see that in terms of left-right forces, we only have Ft1 and Ft2. Ft1 is left, Ft2 is right. So with our reference frame, left is negative, right's positive. So we have Ft2 minus Ft1. Now it's not all of Ft2 and Ft1 because part of those are up. So it's just the component that's left and right, and that's why I put a little x. Just to remind myself it's not all of it. So our final sigma F equation for the horizontal, sigma Fx, is Ft2x minus Ft1x equals 0. Why is the acceleration 0? Because the traffic light's hanging still. It's not moving or changing its velocity in any way. Now you independently have to decide on the signs when you do sigma Fy. Sigma, or the two tension forces were in opposition before, because one was left and one was right. But in the y dimension, they're both up. So that's why I have Ft1y plus Ft2y. Gravity's down, so it's minus Fg. This is the equation for the force of gravity, mg. And again, we don't have any acceleration as the thing's hanging still. So to make this seem a little more real, we're going to play with something called a force board. And a force board lets us add these forces by pulling on springs and seeing how big the forces are. Let's take a look at one. It's a big metal disc. It's got notches in it. And on those notches you can put these fish scales. Let's zoom in and take a look at one. If I pull it, you can see there's a spring inside. And the more I stretch the spring, the more that little arrow goes down the scale. It's measuring the force on the spring. So the ring's not accelerating. It's standing still. Its motion is constant. And what that means is that in all dimensions, there must be no net force. The force has to add to 0. Sigma F is 0. So what dimensions are there? Well, it's a plane, so that means 2. And we can specify the x and y axis however we want. So I made a little reference frame here. And I'm going to make this my x and y axis. In other words, the two scales currently hooked up are along the y axis. And I'm going to pull this guy, and you in lab are going to pull this guy towards the right. So let's look at what the scales are currently doing. As you can see, they're reading about the same. They've already got some force on them, and that force is equal, showing that all the upward force from this one is being canceled out by downward force from that one. So this shouldn't be surprising. We have no forces in one dimension, and in the other dimension,
we just have our forces canceling. So 3.9 newtons up, 3.9 newtons down. That sums to 0. What we're going to do now is grab this third scale and pull it straight along the x dimension.
But look what happens if I pull the third one to the right. Obviously all three scales increase. But now the two that were just pulling up are now pulling back to the left. But they're still pulling up or down. And that's kind of the key thing. This rightward force, because the ring is not moving, has to be canceled out by a leftward force. Where's the leftward force coming from? The two scales that were previously just up and down. Now they're still up and down, so they also have to be providing forces in that dimension. So the two original scales are doing two things. They're both providing leftward forces and upward forces, and downward forces, I guess. So how do you keep track of all this? How do you see what part of the two original forces goes to combating the new force? You have to do a sum of force equation in each dimension, and that's what you're going to be doing in lab. The process starts pretty simply. You draw your forces and you write sigma F equals ma for both horizontal, which has an x after the F to show horizontal, and vertical, which has a y, the x and y axis. In general, you're always going to draw the forces and write sigma F equals ma for both dimensions. In this case, the reason it's 0 is because the ring in the middle was not accelerating. So all forces in both dimensions have to cancel. Typically, one of the forces will be unknown. Here, everything's known, and all we're doing is checking to see that these forces really add to 0. So first step is draw your picture. Write sigma F equals ma. The next step is going to be to start listing the forces that act in each dimension. So let's zoom in and see what that looks like. I like to use the words up, down, left, right to describe each force. Notice I've drawn my axes. We're going to call up, down, y, left, right, x. So the three forces, F1 is left and up, F2 is left and down, and F3 is right. So I've coded in red left and right. If we go over here to sigma F, you can see what I put here. The rightward F3 minus the leftward F1 and the leftward F2. Notice F2 and F1 have an X after. And that's to signify that it's not all of F2 and F1 that we're talking about, just the part that goes left. Right positive, left negative. If we go over to our Y forces, we see F3 is missing because F3 doesn't have an up or a down. So we have the up minus the down. And notice these are Y's because it's only the Y part that we care about here. So that's step 2. Step 3 is to start trying to get these F1x, F2x, all that stuff. We do that by taking each force that's at an angle and turning it into the hypotenuse of a triangle. The sides of that triangle will correspond to what we're looking for. Here, F1x is the left part of F1. F1y is the up part of F1. So now these labels that we had in our two sum of force equations, they're actually now on our picture. And we're just going to use trig to try to solve for what these sides of the triangles are. So if we look at how we solve for this, we see that we write sine and cosine for each angle that we're interested in. I've called the angle here theta for F1, and I've given it a different Greek letter, phi, for F2. And so these over here have to correspond to the top force, these correspond to the bottom force. Let's zoom in and take a look. So by writing sine and cosine, you actually get two equations, one which has the unknown f1y in it, and one which has the unknown f1x in it. Since sine theta and cosine theta are just numbers, these are really solvable equations. We can get f1y and f1x directly. And similarly with f2y and f2x. All we need is sine theta and cosine theta. So here's our final answers. And F3 just got plugged in full, and then the orange side of this triangle gets plugged in here. The teal side of the bottom one gets plugged in here. And we can see that we get about 0. The 0.46 is significantly less than any of the actual forces we were looking at in the lab. And a similar thing happens over with vertical. The brown side is 7.4. The pink side of this one is 7.99, so we get about 0 again. I wanted to do one last thing with the force boards. I think it's fun to pull that rightward force more and more and see how the two diagonal forces have to respond. Because in the lab, again, you pulled that right spring scale more and more to the right each time. And as your rightward force increased, that meant that the two forces that could pull leftward also had to increase. Like any new type of physics problem, this is going to make the most sense if you practice it. So I want to demonstrate one more problem, and then we'll give you guys a chance to practice. So it says you push a car with a 300 Newton force directed at 17 degrees below the horizontal. It gives you a resistance force. So this would be like if you're pushing a stalled car. And you're probably not getting down and pushing straight, you're probably pushing kind of down on it. So that's how we're going to deal with the angle. This problem, like every other, follows the same steps we do for 2D forces. Number 1, draw a picture. Not the best car, but that's okay. Here's our friction force parallel to our road. Of course, we have a normal force. And we have gravity. And here is our pushing force. So that's the hardest part of the problem, is getting a decent picture. We now have to generate a sigma fx and a sigma fy equation. We may not need both, and in this case I think we only are going to end up needing the horizontal. But let's do both. Sigma fx equals ma. So what goes in there? Any force that can be described as left or right. And in this case that's fp and ffr. Of course, it's not all of fp because fp is also partially down. So we're going to put an x on it to signify just the part of fp that's going to the right and not the part that's down. We could do the same for the y. So Fn would be up, so positive, minus Fg, and then minus Fp, the part of Fp that's down. So we'll call that Fpy. Honestly, if you could do this part, you're kind of home free. That's the hard part. The next step is any force that's not purely left-right or purely up-down. We use trig to break it down. Obviously, that's just Fp. So we find the part that's left-right. We'll call that Fpx. The part that's up-down, that's Fpy. And they told us that this angle was 17. So you can find both of these just using sine and cosine. So I'm going to just stick with x for now. I don't think I need y for this problem. But in general, you would do both the sine and the cosine. Since Fpx is the adjacent side, I'm just going to worry about cosine. And the cos of 17 is going to be Fpx over FP. So just solving for FPX by itself, I'm just going to multiply both sides by FP, and I get FP cos 17 equals FPX. I can now put that over here in this equation. It gave me what the frictional force was. I know the mass of the car. So the only thing I don't know is acceleration. So now, once I do this, I'll be able to solve for that acceleration. Notice I didn't have to do anything with the y equation. Sometimes you do and sometimes you don't. Typically what I would probably solve for here would be the normal force. To solve the second part of the problem, how long does it take to go 5 meters? I would finish this by getting the acceleration. And once I had the acceleration, I would look for something that has distance, time, and acceleration in it. And we know that equation, of course, is x equals xo plus vot plus 1/2 at squared. And I would plug into that and solve the problem.
So I didn't want to sit there and make you watch me do all the math on the board. But just a quick summary, I plugged in for FP, I plugged in for cosine of 17. I was able to solve for acceleration. And then to figure out the time it would take to go 5 meters of pushing, I just plugged in that acceleration and that distance and solved for time. Much like projectile motion, these problems can look pretty intimidating because there's a number of steps, but if you follow them all, you'll be good. Free body diagram, sigma fx, sigma fy. Any force that's a diagonal gets broken into its horizontal and vertical components, and then you just, what happens at x stays in x, what happens at y stays in y. It's like you're solving two different problems, just like projectile motion.